Hello and welcome to my next video that will explain how to approach a very tricky question, a couple of difficult questions from the GMAT official guide diagnostic test. We're going to be talking about question number 11. And once again, for those of you curious about what kind of stuff I have in my UQR training class, in my GMAT training manual, the table of contents, you'll see under the top 14 triggers, number 13 is where they ask this question, how many different how many different arrangements, how many different orderings, okay? This is a counting problem, which I'll refer to in just a minute. And that's what we're going to take a look at, and you're going to see we're going to create labeled slots and use factorial logic. It says or apply n choose k. We're not going to do that in this particular question. In addition, counting problems, and that's stuff like combinations and permutations and all that kind of good stuff, okay? The main trigger is when they ask for how many of something, how many arrangements, how many orderings, how many ways, and that's what this question does. Notice in the question, how many? This is definitely a high level question that I'm going to discuss. And just as a reminder, I'm not going to teach kind of how to do it. What I want to remind you is I'm going to show you how a UQR graduate would end up attacking this question. And if you want to know what the hell I'm talking about for UQR, you can check out my very first couple of videos that discusses that class. So this is definitely a tricky question. It's the diagnostic question number 11. Let's take a look at a more full screen and let's attack this bad boy. So it says, of the three-digit integers greater than 700, how many have two digits that are equal to each other and the remaining digit different from the other two? Now, what the official guide does is they just sketch out all of the possibilities. That's certainly not wrong, but there is actually a mathematical way to do that, and it can be found in my UQR course, which is not quite ready for prime time, but will be shortly. And here is how a graduate of my course would attack this particular question. The first thing he or she would do, and it's similar to probability, is to kind of lay out the number of elements that we have. In other words, here we have three digits, and we're going to use slots. That's just step one. And yes, this is similar to probability. Okay, the more uniform the methods, the better. Step two is to label these slots, these events, with one example of what we're looking to happen. So one example of what we want to happen, one example would be the first two being the same and then the third one being different. And this is classic. They love these same and different ideas. So you definitely want to be looking to label your slots like this, same and different. S and D. That's step two, labeling the slots with one specific example of what we're looking for. Step three is to label each slot with the number of possibilities for that slot. That sounds a little bit weird, but like for example, this very first slot here, how many numbers could go first here? That's what I mean. How many numbers could go first? Well, if it's greater than 700, going back up to the question, right? That means that the first digit could be a 7, 8, or a 9. So we have three possibilities. Now here's where things get conceptually tricky. How many digits are the same as this first digit? Well, only one, right? There's only one digit that's going to be the same as that. I know that's a little bit tricky. And then, in terms of different, this is also tricky. How many digits are different from these two? 9. Because we have a total of 10 digits, right? 0 is a digit. We're not done. This is still part of our step-by-step process, step 3, which is to multiply across. So we multiply across and we get 27. Okay. So it turns out that this 27 is the number of three-digit integers greater than 700 where the first two digits are the same and the last digit is different. Specifically, that's what that 27 represents. However, we might have other possibilities. So this moves us into step 4, figuring out how many different types of three-digit integers greater than 700 can we have where two are the same and one is different. So, for example, I have, this is here one possibility, but I could also have SD DS, right? Same, different, same. That's another possibility. And then the final possibility is different, same, same. So three possibilities. Now, I will come back to this idea, like what if I had 7 digits and there was a lot, can I always sketch out the possibilities? There actually is a counting method to use for that. I'll come back to that momentarily. But what you need to know is step 5, I now have to account for. Step 5 is to multiply this 27 by the number of ways I can have that, because I know that each of these ways, this is 27 different ways, this is 27 different ways, this is 27 ways. So that's why step 5 is to multiply the 27 times 3, which gives us 81, which is, oh, not among our answer choices. Oh, wait a minute, not a big deal, because I know how this test works. Sometimes they do this. If we think about it a little bit, the answer has to be 80. Why? Because this 81, this 1 itself, it includes 700 as a possibility. But we know from the question it has to be greater than 700, so we have to get rid of that one possibility, meaning again, has to be 80, answer choice C. So that's how to approach this very difficult counting question. Real quick, going back to what if it were like, I don't know, a 5-digit integer, and they had like the three of them were the same and two of them were different. There's actually a very basic formula for determining that, but that's kind of beyond the scope of this particular video. I don't want to worry about that now. But the formula is 5 factorial over 3 factorial times 2 factorial. Okay, that would give you 10 different ways. But that's something we learned in my course, and this is not combinations, by the way. This is not combinations. Some people call it anagrams. I call it rearranging letters. That's actually beyond the scope of this particular lesson. I just wanted to demonstrate again, I really believe in the power of my course, and somebody graduating from my course would see this is how to approach this question quickly, quietly, and efficiently. So I hope this was a help, but let's take a look at actually another question, which I actually think is even more difficult than this question. I think this question is real hard. I think the next one is quite possibly the most difficult question in the diagnostic, I guess, depending on how you look at it. So let's take a look at that, please. Okay, so again, GMAT official guide. Any of these, it's all going to be the same because the diagnostic test always remains the same. And now we're going to take a look at question number 13. And then from my GMAT training manual, you're going to see we're talking about number properties, specifically when they use the word remainder, because we have the word here, remainder. That is our trigger. And this one definitely gets a little bit, definitely very tricky, because there are some other kind of GMAT ways you need to know to look at this. And so let's kind of open this up a little bit and take a look at how we're going to do this. All right. So it says if S and T are positive integers. By the way, all the information they provide is relevant. That's important, and you'll see why in a minute. Such that S divided by T is 64.12, which of the following could be the remainder when S is divided by T? Okay. So what my students know, first of all, is if remainder, you always want to first try to pick numbers or plug in the answer choices. Definitely want to try to do that. However, you can't do that here. Okay, always want to try to do that right off the bat, but one would recognize fairly quickly that can't be done. In that case, one has to use the formula for remainders. And believe it or not, we actually learned this in what, 3rd or 4th grade. And what you need to know is that the basic formula is a remainder is equal to the decimal. What I mean by the decimal is 0.12 times the divisor, which is T here. So in other words, we can say that R equals 0.12T. And you might be thinking that, how is that going to help? Well, let's clean this up a little bit. Students of mine will know we actually have another trigger here, which is a decimal. And I know anytime I have a decimal or anytime I have tricky numbers, I want to kind of break that out. And I can break that out by using 10 to the negative x and prime factoring. Okay, the test loves, GMAT loves this, and anytime we have tricky math, we want to use prime factoring or some kind of version of 10 to the x or 10 to the negative x. So in other words, this is going to be R equals 12 times 10 to the negative 2 t. Prime factoring that will give us r equals 2 squared times 3, that's 12, times 2 to the negative 2 times 5 to the negative 2, all times t. So that's a little bit quick that I did that, but again, the prime factoring. Now I can clean that up a little bit, get rid of the 2 squared and the 2 to the negative 2. So I have r equals 3 times 5 to the negative 2t. Cleaning that up, r equals 3t over 25. Now, as I discussed in my very first video with UQR, here I have a fraction, right? Anytime I have a fraction, I'm going to eliminate that fraction. So if I do that, I mean, why? Because the GMAT wants me to, that's why. So 25r equals 3t. And I'm like, well, what in the world is going on here? Well, let me take a look at my answers, and I notice my answers have all numbers in them. And that's actually a trigger. That's one of the top 14 trigger. And this is very advanced, very advanced. But when you get stuck, so often what you can do on the GMAT is think in terms of what I call multiple and factor logic. So this is going to be tough, but this is classic what to do on this test. So here's the deal. It says 25r equals, right, 3t. Well, you know what I know about 25r? I know that 25r itself has to be a multiple of 5, right? Has to be because 25r. 25 is a multiple of 5. And I know that 3t has to be a multiple of 3. Well, since they are equal to one another, right, because it says it's equal, that means that this 25r also has to be and also a multiple of 3. And by the way, 3t has to be a multiple of 5 because they're equal, right? Well, here's the deal. 25, this 25, that's not a multiple of 3. There's no way. That's not a multiple of 3. So therefore, r must be a multiple of 3. And you're thinking, no, that can't work. Well, if I go to my answer choices, answer choice A, that's not a multiple of 3. 4 is not a multiple of 3. 8 is not a multiple of 3. 20 is not a multiple of 3. Oh, there's E. The only answer that is a multiple of 3. And in fact, that is how to do this question. They want you to understand that. Notice, did I prove that the remainder is definitely 45? I did not. And you know what? Going back up to the question, it says could be the remainder. They're not asking, oh, solve for the remainder. They're asking what could be the remainder. Okay, so this is a very tough question. It requires you to know how to manipulate this remainder formula as well as prime factoring and using 10 to the negative x, which often goes hand in hand. But then once you get down to that, it often requires you to use this multiple and factor logic, which is something you always have to keep in the back of your head. And that's why this is a very difficult question, without a doubt. I find it to be one of the most difficult questions in the entire official guide. Oakley dokley. Well, that brings us to the end of this video. Thanks very much for watching. I really appreciate your time. I hope that this helped you in your GMAT studies, and I hope to help you enough that you'll check out my other videos. Thanks again.